Thank you very much to everyone for coming, and thanks a lot to my host for inviting me. I think the introduction was unnecessarily generous, but it's good to be sort of home. I mean, I still consider Boston area to be my home. We were just discussing over lunch, somebody would say MIT is in Boston. Like, no, MIT is not in Boston, it's in Cambridge, right? And so for me, still like saying something, MIT is in Boston, I object to that. So I still feel like I know the place quite well, even though a lot of new buildings have appeared. So I cannot really find my way around, but I can claim I know the place as long as somebody is leading the way. So anyway, so thank you for being here. I'm going to talk to you about entropy as a concept for studying some problems having to do with state estimation and model detection, in particular for studying minimal amount of data that's required for solving these problems. So that's sort of the general theme that we've been pursuing over the past few years. And so the motivation comes from considering in the feedback loop, in addition to standard ingredients like a plant and controller, the role of information processing devices. So rather than showing a feedback loop like this, we would have a feedback loop that rather looks like this, where you perhaps have a robot you're trying to control and a laptop on which the control signal is computed. But in addition, you have a camera that collects measurements and some wireless medium through which control input is sent back to the robot. And in these types of situations, you start asking questions about what information needs to be exchanged, or how does the information processing that takes place affect the behavior of the feedback loop. So you have to contend with issues like limited channel capacity, encrypted data, some limits, physical or implementation limits on the sensing and actuation. And these things may not be so important if you have a single feedback loop, but if you have a network of systems in which many feedback loops share or compete for resources, then you really have to be more attuned to these things in design and analysis. And the way that we typically address these things is we look at errors that arise due to transmitting, measuring, reconstructing signals. And we need to, as control designers, we need to come up with control algorithms that are robust to these errors. This talk, however, mostly will not be about control. It will be about things that come before you can do control, which is, estimate the state, even detect the model you're working with. So I have control in mind, but in this talk I will do very little about control, but more about these two specific problems that I mentioned in the title. One is state estimation, the other is model detection. They sound like very different problems, but I'll actually explain how they can be tackled using similar approaches. And we care about doing these things with finite data rate and understand how much data rate is needed to solve these problems. It's something that I plan to explain in more detail as we go on. So the basic setup is this, that you have a system, you have some sensors that take some measurements, you have a channel over which you encode and send the data, and on the other side you decode the data and use it for estimating quantities like, let's say, the state of the system. And then eventually you use these estimates for control purposes. And the unifying approach that I will explain is based on the notion of topological entropy. It's something that I will define and then show how it bears on these two problems and provides a unifying approach to studying them. So here's the basic question that you can use as sort of initial motivation. If I'm trying to estimate the state of a given system, how much data do I need, right? And the first thing that I could think about is a system that's contractive. You guys know there's an in-house expert, Jean-Jacques Slotin, who has worked on this. So many of you have seen what a contractive system is, but basically it's a case where trajectories converge to each other, right? They don't necessarily converge to an equilibrium or anything like that, but the distance between trajectories decreases. And in this case, from the point of view of information requirements or data requirements for estimating the state, you could say that this case is trivial, right? Because basically, if you have a true trajectory that you're trying to approximate, you can just take any trajectory of the system. So you don't have to ask the system for any data. You don't have to take any measurements. You just take any initial condition, you flow the system from that initial condition, and over time it'll approach asymptotically accurately the true trajectory from an unknown initial condition that you may care about, right? So no data is needed in this case. But of course, in most cases, the situation will be not like this. In general, the system will not be contractive. So you will have trajectories that diverge. And then you can ask the question, how many trajectories or how many initial conditions do I need in order to approximate all trajectories, including the trajectory of interest, whichever one that might be, right? So you have the true trajectory that I show in red, and I take a bunch of initial conditions, and there's going to be one shown in green here, right, for which will be close to the actual red trajectory, at least for a while, right? So that means that in a sufficiently small tube around the green trajectory, my true red trajectory will be contained for some period of time. So I need to make this, and I will make this a little bit more precise later on, which means that there are some parameters associated with this. The size of the initial tube, the time horizon over which this approximation is valid. Also, you might notice that I made this tube shrink exponentially over time slightly, so there is this rate of change of the width of the tube. That's another parameter that defines this approximating property. And so these parameters translate into data rate that's needed to maintain this approximation, right? So the data, by the way, keeps coming, right? So I make a measurement, I find this green trajectory. After a while, you see that this red trajectory will escape the tube. So I have to ask the system for more data at that point, right? So data rate has to do with how many bits per unit of time need to be transmitted in order for me to keep track of this red trajectory by the sequence of green trajectories and tubes around them. And this relates to this notion of entropy that I'm about to discuss, that sort of conceptualizes things and makes it possible to relate the data rate that's needed to some properties related to the system itself. Okay, so that's sort of where we're going with all this. And so let me go to define this entropy notion. So I listed some references on the bottom. So this goes back to very classical work, 1940s, 50s, by Kolmogorov and others, that has to do with just dynamical systems. There's no control there, but the ergodic theory of dynamical systems. And then some of the other references, some of the other people mentioned on the bottom here are groups working in control theory that have used this older work but reformulated things in a way that's more compatible with control scenarios. So let me try to define entropy. So we have a system, just a general nonlinear system, a state in Rn, and I take initial conditions from a known compact set, K, and I will write psi x of t for the flow, right? So psi is a solution at time t, started with initial state x. And I will pick these three parameters which relate to the quantities I mentioned in the picture on the previous slide. So I will pick a time horizon t, capital T. I will pick the resolution epsilon, that's the initial size of this tube that we had on the previous slide. And I will also, and this third one is kind of not the classical, not part of the classical formulation, but it's what we did in this paper, is we pick this desired exponential convergence rate. So that's the rate at which this tube gets smaller over time. So we want the estimates to actually be refined over time. That's a constant alpha. If you pick it 0, then the tube remains fixed in width, and that's a perfectly legitimate case to think about. So if you want to ignore this alpha, set it to 0, you can do that. And then we say that a set of points or initial states in the initial set K is spanning, and it depends on these parameters t and epsilon, as well as actually an alpha. I'm just omitting the dependence on alpha for convenience of notation. So it's t epsilon spanning if for every initial condition in K, you can find one point x sub I from your set, so that the trajectories, the one from x and the one from x sub I, remain close over this time horizon capital T. Right? So that remain close is defined like this. So they remain within epsilon times this exponentially decaying factor with rate alpha for this time horizon. Right? So in terms of the picture, they just remain within this tube centered on 1. The other trajectory remains in that tube. And you count among the various t epsilon spanning sets how few you can get away with, right? So what is the smallest cardinality of such a t epsilon spanning set? And we call that quantity little s of t in epsilon. And then if you think of representing the set with bits, right? You have to take the log, and then you also want to do an asymptotic quantity over time as time horizon goes to infinity. So that's how you define the estimation entropy. You take the log of the cardinality, you divide it by time, you take the lim sup over time, and then you also take the limit as epsilon goes to 0, so that you can capture this for arbitrary precision. For the log, I will make a standing assumption, since I have a nice board here, and maybe even chalk somewhere. I will make an assumption for the purposes of this talk that E equals 2, so that I don't make a distinction. I didn't write that, it was just on the board, right? Don't quote me, but just so that I don't have to make a distinction between natural and binary logs, or counting bits versus counting nets. There's just going to be an annoying multiplicative correction factor that I don't want. So, but it's just that, right? Without this assumption, there would be some factors to make results actually correct. My results will be slightly wrong, but correct under this assumption. Okay. All right. So,
just say log to base 2.
What's that?
You could also just say log to base 2.
No, because I don't want that, because then sometimes, because it's continuous time, I want exponential things. So I want sometimes to count actually nats, but I say bit rate. So whatever I do, I can't win. This is the best solution I have to this. But anyway, so what I want to do is maybe unpack this definition a little bit, because if you've seen it before, it's familiar. But if you're seeing this definition for the first time, I don't think it's very immediately intuitive, right? So let's talk a little bit about this using this toy example. So what I want to do here, I want to estimate the state of this very, very simple scalar unstable dynamical system, where I know that the initial state is in some interval. Okay, so and I want finite data rate measurements or encodings of the state to use for estimation. So here is what I do. So this is my initial interval. So at time 0, I'm somewhere in here, right? So I'm going to divide this this interval into n subintervals. I'm going to mark their centers like so. And the encoder at time 0 can tell me which of these smaller subintervals contains the initial state, right? So let's say it tells me that my state is here, right? It cannot tell me exactly where the state is. What it does is really tell me which subinterval. So left, middle, right. So it's going to tell me middle in this case, right? So for my purposes, I'm going to mark the middle point as my best available estimate at time 0 of where the state is based on this information that I received, right? So now at some sampling periods, I'm going to sample the system every capital T units of time. So it's a parameter that I'll fix, this capital T. this interval will become larger because my lambda is positive, right? So now my state is anywhere in this slightly enlarged interval. And now I can ask for more information. So I'm going to do it in the following way. I'll divide this new set, larger reachable set, again into n subintervals. And it's going to again tell me, the encoder is going to again tell me which one the state is in right now. So let's say it tells me that it's here, right? So it tells me that the state has passed from the middle one into the left one of the new partition, right? So then, and I keep repeating this, so then at this time I'll mark this point as my estimate, right? So one question you can ask is, given that I can repeat this, I will generate a sequence of green points. So you probably have in mind now readily what would be the best estimate that I can get based on the sequence of green points, right? I know the dynamics, right? So I'm assuming here that having the first green point, I can propagate the system solution from that. So the best I can do is for the first t units of time, just propagate the solution, then switch to the new point, propagate the solution from there, and so on. So I will generate this piecewise continuous estimate that seems like a sensible thing to do based on what measurements I'm receiving, right? So then if you do this, you can ask the question, how much data does this encoding scheme that is running in the background here, right? How much data does it use? And it uses this many bits per second because it's one of n symbols is sent every t units of time, so pretty simple. And so after L repetitions, we know that the state is in the interval of this length because this is by how much the size grows when no samples are coming, and this is by how much I divide every time the sample arrives, and this is the size, the length of the original interval. So in order to estimate x of t with error that I want to converge at this rate to 0, right? So I'm going to prescribe now this alpha as a desired rate of convergence of my estimate to the true state. Then you can very easily calculate that you need your alphabet to have at least this many values, okay? And so the data rate, which is the log of that over time, is going to be lambda plus alpha, bits or nets, again, depending on which logarithm I take. So you could have probably guessed this at the outset, right? Lambda is my underlying uncertainty propagation rate, so I need to contend with that. Alpha is by how much I want, how fast I want the estimates to converge. So if I add them up, this is sort of, I want to get an improvement from lambda instability to alpha stability, so I need the sum of the two is the data rate that I want. Right? And it turns out you can get, with simple computation, you can get the same exact result with entropy, right? And so that's a good thing to think about if you want to unpack the previous definition of entropy. So a set of points in my interval is t epsilon spanning if they are at most this much apart. Neighboring points are this much apart, right? Because then you will grow at the rate of lambda, and at the end of the interval you will still have e to the minus alpha t left, which is the definition of the spanning property. So then you can easily calculate what is the cardinality of such a set in terms of the length of the interval in which you need to achieve this coverage. And then you perform the requisite operations of taking the log, dividing by t, taking lim sup. The dependence on epsilon will actually disappear in this process, so you don't have to take the limit over epsilon. And you would get that the entropy of the system is exactly lambda plus alpha, right? So the entropy, again, depends on the system. Lambda is the system parameter. But it also depends on your goal of how fast you want to estimate the state. If you set alpha to 0, this is a classical entropy of the system, which for this case is just lambda, is the topological entropy of the system. Okay. So the two are the same, so the entropy gives you this answer. And this is something that is a situation that we want to replicate for, obviously, systems that are not scalar, right? So that's what I want to talk to you about. Perhaps any questions about this toy example before we move forward? Right. Good. So how do we approach this in the general multidimensional case? I want to have some equivalent of this single constant lambda that I had for the scalar system. So, and this is something that we will call expansion rate. And the way that we can get that is, again, if you have trajectories that I'll denote by psi of x and t, then we want to find a constant c such that trajectories from different initial conditions separate from each other at most at this rate, right? So initial distance times e to some positive in general, unless the system is contractive, positive constant c times time, right? So it's not very hard to come up with definitions of this c that will work. It might be challenging to do it globally, but if we confine ourselves to a compact set, for example, if you have a compact invariant set that you know for your dynamics, then this is just a Lipschitz property of the right-hand side, right? So c can be a Lipschitz constant of f over the set of interest. You can do a bit better. So you can take the Jacobian. It's easiest maybe to assume that f is continuously differentiable for this definition, although it's not necessary. And then you can take the Jacobian of your right-hand side and take the matrix measure, which is this known quantity from linear algebra. And you take the supremum of this matrix measure of the Jacobian over the set of interest, and this gives you a sharper estimate of this expansion rate c, if you prefer to work with this. So for various standard norms, you have closed form expressions for this matrix measure. This is something we'll come back to in a few slides. So I'll flash this here for the infinity norm. And the infinity norm is quite convenient for our purposes. You will see in a bit why. Then you know how to compute this matrix measure with respect to that norm. So in any case, whichever approach you take, you have a constant c whose role sort of mimics the role of this constant lambda in the previous toy example. Good. So now, once we define the entropy, maybe the first thing we would like to do is estimate it for a given system, come up with some lower and upper bounds that are maybe easily obtained, whereas the exact value of the entropy from the definition may be challenging to compute, right? So here I'm just copying on the top the data that we had. And so here's an upper bound. For the given system with right-hand side f, for which we have these quantities, so c, again, is the expansion rate. It's something that satisfies this bound. Alpha is the exponential convergence rate that we hope to have. N is the state dimension. So if you form this expression, that gives you an upper bound on the entropy. And I'll just very quickly give you an idea how this is proved. I don't want to get too technical here, but you're basically counting balls of this radius, how many of them you need to cover your initial set, right? Because that's what this T epsilon spanning set is how many centers of these balls of given radius will cover your initial set. And even though you can do this in general to get the right answer more quickly, you can make a simplifying assumption that we're working with infinity norms. So all these balls are actually hypercubes. And let's say that this initial set K is also a hypercube. I guess a unit hypercube is the easiest case. So then it's very easy to do this computation. You need this many per dimension. And so when you take the log, divide by t, you would arrive at this bound. The entropy can never be negative, so you have to take the max with 0. This comes out to be negative, and that gives you the upper bound. And like I said, the answer is true in a more general situation than the one I'm exemplifying here. For linear systems, it's quite well known that you can refine this. So the right-hand side can be taken to be the sum of the real parts of the unstable eigenvalues when shifted by alpha. And it's not actually an upper bound. In this case, it's exact equality. So you can show that this right-hand side also serves as a lower bound. And the way you show that something is a lower bound for the entropy is typically by some volume counting argument. So you take a volume of the reachable set from initial set at time t, and use Liouville's formula and count how many balls you need to cover this volume, at least how many balls you need to cover that volume. So it gives you a lower bound. And in the linear case, they coincide, so you get an exact expression. But using a similar argument, you can also get a lower bound for nonlinear systems, and one possible lower bound looks like this. So you take the Jacobian, instead of the matrix measure, you take the trace, and you take the infimum over the set of interest. This may or may not be a useful bound. It may come out to be something like negative or minus infinity, but in case it comes out to be positive, it gives you a useful lower bound on the entropy. Okay? So these are the types of things. There is quite an extensive literature on estimating entropy for various systems with specific structure, which is not something I'll do here today. But here is one example. So we have this Lorentz system that's quite famous for modeling atmospheric convection, displays chaotic behavior for some values of its parameters. The equations are like this, and you can do computations. So for a given initial set, which is a ball of some radius around the origin, you can use Lyapunov analysis to show that all solutions are confined to another ball with a different radius and whose center is shifted based on the parameters of the system. And then all you have to do is compute the Jacobian and take the maximum of the matrix measure, which is this expression here, over this ball of radius r. And you can come up with, that way you come up with an expression for this expansion rate c. It's something that looks like this. And so the upper bound tells you that you have to add to it the exponential rate at which you want the estimates to converge to true states. You multiply by system dimension, which is 3, and that gives you an upper bound. Is this upper bound good? No, it's terrible. Okay? But it's an upper bound. So from that, you can try to refine the analysis to compute something that's less conservative, but you get some result in this way. Okay. So now let me talk about sort of the operational meaning of entropy. What can we do with this? And now I'll finally come to talking about the problems that I posed at the beginning, one of which is state estimation, right? So again, this is a setup, and you have the system dynamics. You sample the state using, yes, question? Slide 7. I'm cheating slightly with my slide numbers.
I think it's previous.
Before, okay.
So maybe
This?
correct.
Yeah.
So these are also standard definitions for contraction, right? And if the contraction rate, and if the
Sure.
contraction rate is negative, then it's expanding, right? So now in contraction, you can also put metrics, right?
Right.
Would that be useful here, or would it distort the entropy computation, or?
So I think it would be useful. So like, you know, Francesco Bullo has done some work where they played with different metrics in a similar context. For me, I'm just trying to keep things simple. So I think I could refine some of the results,
Yeah,
but yeah.
The contraction metric gives you a much more precise rate, right?
Right.
Then, of course, it corresponds also to differential coordinate change. It may change the station eventually. That's why.
Right. But you would have more than just one constant, right? You would have just one constant would be the answer.
It's just saying, I mean, the most trivial way of seeing a metric is just a coordinate change, right? The normally coordinate.
Right, right.
So then in the new coordinates, the rate is different. Right?
Okay, yeah. So I think there is some room for definitely for making this, for refining this. Yeah, I agree. Yeah, thanks. Yeah. All right. Any other questions, by the way, so far?
Do you
Yeah.
have any dependence on which norm you choose in the matrix measure?
So the matrix measure, the expression will change. But other than that, the way I'm presenting it, you know, any norm will work, but the actual number that you get, if you get a number for the matrix measure, will be different. But the entropy, so the way I define the entropy is it depends on the norm, and I'd have to think about it. I believe that you can show that the entropy is independent of the metric. But so there is basic result on that in Katok's ergodic theory book. But I think I need compactness for that, and so I'd have to think carefully. Maybe unless I have compactness of my state space, I cannot show independence. So maybe some multiplicative factor will creep in. Yeah, I'd have to think about it. But at the level of formulation, whatever norm you want, you fix it, and then the formulation doesn't change. All right, good. So I'm going to sample the state with some period, capital T. I'm going to send some encoded quantized value that at step I, I'll call it Q sub I. The channel will be something trivial, right? For those of you in the house who are information theorists, nothing interesting happens. I just can transmit this Q sub I symbol from a finite alphabet perfectly to the other side, right? So the only limitation is the bit rate has to be finite because these are quantization symbols that are being sent, but they're sent perfectly. And then on the other side, I have to reconstruct an estimate that's valid over the next sampling period, right, of length capital T. So this is fairly standard by now algorithm. I'll just maybe illustrate it with this animation here. So what you can do is you cover your initial set with a bounding box. Let's say that it's a hypercube. So although I could refine it and have it have different size in different dimensions. So then I partition it into smaller boxes, and I will ignore these constants, but there is a specific expression you can work out for how small you want these boxes to be relative to the overall box. And the encoder, if it knows that the initial state is here, it signals to you that the initial state is in this box. So that's the information you receive on the decoder side at time 0, right? So then you have to flow this box. So the green trajectory will be your estimate for the next sampling period, right? Because your best estimate is the center of the box that's being signaled to you. But the box itself will evolve, right? So the image under the flow of this yellow box over here at the next sampling instant will be something like this, right? So it's something, maybe the shape is ugly. We need to cover it with, or over approximate it with, again, a hypercube. If you choose to work with hypercube, you can work with different shapes if you want, but here I work with hypercubes. So I repeat this construction. I have the bounding box S1, and I partition it again into smaller boxes. And you see in this contraction factor, I leave room for exponential convergence at rate alpha. And the C accounts for the expansion, the natural expansiveness of the system. So if the actual initial set leads me to a trajectory that ends up here, then at this new time, I need to reset the estimate to this new center, because the encoder signals to me that that's the box that contains the state. And then from there, I repeat, right? I build an estimate, which is a trajectory propagated from this new center, and I repeat the procedure, right? So the properties that it has basically by construction, if nothing went wrong, are that at each step I, my state is indeed in the bounding box. So my estimate does not generate garbage, right? It's actually one of the boxes contains it. And the other is that the estimation error taken in the infinity norm converges at this rate, right? So as required by what we wanted to do. So, and then you can, because we're interested in the data rate that this uses, you can calculate the data rate used by this algorithm. That's routine to do. So you know the size of your alphabet. So you know that the bit rate is 1 over t times log of that alphabet. It actually comes out, not surprisingly, to be exactly the upper bound that we got on the entropy, right? So it's c plus alpha times n. So in fact, to show why this is true, you have to be a little bit careful and say that quantization points define a spanning set, and over L rounds, the number of possible code words is cardinality of this spanning set over the corresponding period of time. And so if you calculate the bit rate, it cannot be smaller than if you were using the smallest spanning set And that expression in turn converges to the entropy. So what's going on here is we're using a specific spanning set, which is this grid. It's a spanning set, it's not the smallest one. We don't know what the smallest one is, right? If we were using the smallest spanning set, we would get exactly the data rate to match the entropy, because we're using something a bit easier to work with, but potentially suboptimal. There is a gap, right? So the entropy is the theoretical minimum for the required data rate, but the efficiency gap is the difference between the upper bound on the entropy and the actual entropy, right? And that's the price we pay for having a constructive procedure, right? And if you chose some other geometry for the sets, you may be able to improve on this, but you can never do better than the entropy itself, right? So that's the data rate usage of this algorithm. Now, let me bring in this model detection problem, which, like I said, it sounds like it's very different, but it actually falls very nicely into the same framework. So let's bring in the following aspect, that I don't actually have full knowledge of the model of the right-hand side of my system. But let's do it in a limited way, just for illustration purposes. So let's say that I have two competing models for what my system can be, right? F1 of x and F2 of x. They're both known, but I don't know which one I'm dealing with, right? So using finite data rate state measurements, as before, I want to distinguish which one I have. Of course, I will not be able to do it if the two systems are the same or almost the same, right? So I need to have some notion of these two systems being far enough apart, and we can define it in the following way. So if we take the data, let's say for system 1, the setup is slightly asymmetric here, which is okay. So C1 is expansion rate of that system. Then we will call the two models separated if there exists the threshold epsilon star such that the following happens. If you take any epsilon smaller than epsilon star and you pick two initial conditions within epsilon of each other, and you consider solution of system 1 from x1 and solution of system 2 from x2, and you look at these two solutions after time t, they will be at least this much apart. Okay? Then you say that they're separated. And the motivation for this is that if instead of two different systems, you ran the same system from x1 and x2, let's say system 1, then because C1 is expansion rate for system 1, the inequality would go the other way, right? So the interpretation is that if this happens, then you know that these trajectories could not have come from system 1 because they would not have been this far apart after t units of time, right? So it gives you sort of a measure of separation between two systems and a way to use it to distinguish between them. So we've looked at the separation property. It actually is not too bad in the sense that it holds in some sort of generic sense, at least over short periods of time, and you can find details in our paper. But the way you can now use this in the algorithm is the following. So you essentially run the same algorithm as on the previous slide. You feed it model 1 as hypothesis. And the claim is that if the model 1 is incorrect, it will eventually falsify it. And what would happen, just informally using a picture, is you would run this algorithm that will generate these boxes. Eventually, the boxes will shrink to within this epsilon star that we used in defining separation. And at that point, if the model you're using is actually wrong, at the next sampling instance, the state will be outside of the box. You'll get an error. And you know you cannot get an error if the model you're using is correct because the algorithm is correct by construction. Because the models were separated, you do generate an error, and at that point you will say model 1 is incorrect, the correct model is model 2. Obviously you can do it if you have more than two models, but still the only thing we know how to do is if the set of models is discrete. Otherwise, if it's a continuum of models, things become a bit more challenging. You also don't know how many steps it takes until detection unless you have some information about this epsilon star. So if you have some prior knowledge of this epsilon star, then after corresponding number of steps, you're sure that the model you are given as hypothesis is correct. Okay? So that's the model detection part. I have maybe like a couple of minutes left, plus time for questions. So let me just very briefly say that there are two directions of recent interest that we're pursuing.
Sorry,
yes.
one question about the previous
Please,
part.
go ahead. Yeah.
So, I mean, if I understood it correctly, this is not discriminative in the sense that, you know, there are pairs of models that can be distinguished by other things than their contraction rates, right? That this wouldn't distinguish between.
Yeah, I think that's right. So it's a sufficient condition, the separation property is a sufficient condition for me using this method to distinguish these two models, right?
Okay. Okay, thanks.
Yeah, so one thing that I'm not using a probing input with some kind of persistency of excitation property. So I think I do believe there are meaningful classes of systems for which this would work well, and maybe some existing methods would not. But the converse is definitely true as well, right? So, fair point. Yeah. So for interconnections, I mentioned that we're interested in sort of looking at networks of systems, right? And so why don't we use that type of structure to try to refine our entropy bounds, right? So let's say that we represent our system as interconnection of k subsystems of smaller dimension, right? And you have these corresponding blocks of the Jacobian matrix. So you can then put some more structure into this. So let's assume that there are these numbers aij, which upper bound matrix measures of diagonal Jacobian blocks and induced norms of the off-diagonal Jacobian blocks. Then we build this structure matrix by using these aij's. It's a Metzler matrix. So off-diagonal elements are non-negative, so it has the largest eigenvalue that's real. And then you can prove this entropy bound, which is that the entropy is upper bounded by this eigenvalue shifted by the desired exponential rate multiplied by system dimension. So it's a similar looking bound, but it's a bit refined compared to the general bound that we had. If you play, for example, with this Lorentz system that I showed earlier, we can view it, of course, as interconnection of three scalar subsystems, and you can do the computation. You take this Jacobian. I already mentioned we have this invariant set in which we stay, so you come up with this matrix. You can take it to be this, and you compute its largest eigenvalue, and the previous result gives you an upper bound on the entropy. It slightly improves, for this example, the previous general bound that we had, but still doesn't quite give you a bound that's close to tight. There is actually very nice analysis of this particular system in this paper that gives you a tight bound. Our bound is still sort of several factors higher, but it does lead to an improvement over the general approach. So one direction we're interested in is understanding of entropy of systems composed of smaller subsystems and relating the entropy to entropy of the smaller subsystems. The other, so Chu in her very kind introduction mentioned some work on switch systems, so I felt like I have to include something on switch systems so you guys would complain, right? So we're working now quite actively on entropy of switch systems. And so these are the systems, by the way, where you have several modes indexed by some index set p, and then you have some switching signal, which is piecewise constant function of time, taking values in this index set, and it tells you which mode is active at which time, right? And so we used it a lot for purposes of switching control. You can define entropy for each fixed switching signal in the same way as before. It's a time-varying system, but the entropy definition basically translates, remains the same. In order to estimate entropy, it turns out it's useful to define these switching-related quantities like the activation time of each mode and the proportion of time that each mode is activated, which we can call active rate. And then for example, for a switched linear system like this, you can establish these upper and lower bounds for the entropy. So it's sandwiched between weighted averages of system-related quantities. On the left, you see traces of your matrices. On the right, you see matrix measures times system dimension. And the weights are these asymptotic active rates for each mode. So this is a type of result that you can show for the linear case. And there are also extensions for switch nonlinear systems that are in our very recent work. And there is an interesting research direction here, which is there are some results for controlling such switch systems, linear and possibly even nonlinear. And so these bounds can inform control design in the sense that they tell you the minimal possible data rate, which is the entropy, that you need to stabilize these systems. We have some algorithms that use some data rates to stabilize the system, but the data rate is much higher. So it gives us an idea of how big the gap is and what we need to bridge. Okay? And with this, I'll close, and I will not bore you with going through all the points here. But I'll just say maybe the most recent ongoing work that we do is applications to simultaneous localization and mapping. So something I didn't mention is where maybe you have uncertainty about even the measurements. So maybe the measurements reflect some distance to a landmark, but we don't know where that landmark is. So you have to contend with uncertainty, not just about the measurements, but about the sensors or mechanisms which generate these measurements. And so we're now playing with my colleagues, and we're playing with some extensions of this work to that scenario among some other things. So I think in the interest of time, I'll stop here and thank you for your attention.